In this video, we will learn about particle motion, more specifically particle motion in one dimension, and usually this happens along the x-axis. We will learn about the three main parts of particle motion, which are position, velocity, and acceleration. Oftentimes in problems, these will be denoted by the variables x of t. X is the position. It's along the x-axis, so it's really the x-coordinate. And here, all of the independent variables are time. Velocity is usually v of t, and acceleration is usually a of t. So we'll learn about those three and the relationship between them. We will also learn about three other things: distance, speed, and how to tell whether or not a particle is speeding up or slowing down. If you notice, I did color coordinate these because there's a relationship from position, velocity, acceleration to distance, speed, and speeding up. They're not the same, but there's a relationship here, and we'll talk about that later in the video. A brief definition for position. Position is basically where the particle is at a given time. If you think about driving on a highway, perhaps your position is your mile marker number. So if you're on I-10 or I-35, and you pass mile marker like 237, that's your position. You're at mile marker 237. It doesn't tell you how fast you're going. It doesn't tell you how much you're speeding up or slowing down. All it tells you is where you are. In math and calculus, usually your position is directly related to your coordinates. And in this case, because we're only talking about position along the x-axis, it's really your x coordinate on the x-axis. You've probably heard of velocity. Velocity is how fast your position changes. So really it's the change in position over your change in time. And calculus has a great way of expressing this because the velocity is your change in position, dx, over your change in time, which is dx dt. And we'll see very soon that basically this is the derivative of position, which is a very nice thing. Going back to the highway analogy, your velocity would be what your speedometer says. It's how fast you're going. So how fast you're going. Okay. We've also all probably heard of acceleration, and if you think about it in your car and you're driving 50 and you want to change your velocity, then you either hit the brake or you step on the gas. And so acceleration is how fast your velocity is changing. And again, this has a really nice way of denoting this in calculus. The acceleration is going to be equal to the change in velocity over the change in time, and this ends up being the derivative of velocity. So it's pretty straightforward in terms of how you find them given formulas. So I like to imagine this chart. Okay, you have position x, you have velocity v, and you have acceleration a. And this is very similar to the fun chart where you have f prime, and f double prime, because to go down this list, to go from x to v, you take the derivative. And to go from v to a, you take the derivative. And similarly, going backwards, to go from a to v, you're going to integrate a. And to go from v to x, you're going to integrate again. So the same relationships that we have between f prime, f double prime are the same between position, velocity, acceleration, because they're all derivatives of each other. Now earlier we had our fun chart that said like f concave up, concave down, f prime increasing, decreasing, f double prime plus minus. This still applies, but there are going to be some additional things that we're going to look at with particle motion, and not everything in this chart will apply. So keep that in your mind because it's useful for other problems, but as a general thing, the following relationships will be more useful. We have x, v, a, and really one of the only things we're concerned about is what happens when velocity is positive or negative. So by convention, if velocity is positive, that means that the particle is moving forwards, and on the x-axis, forwards means moving to the right. So if velocity is positive, the particle is moving to the right. And similarly, if the velocity is negative, then the particle is moving to the left. That doesn't necessarily mean that the x position is positive or that the x position is negative. It simply tells you which way it's moving. Because you could have 0 here, you could have your particle here at like 5, and it could be moving backwards, and that would have a velocity that would be negative because the particle is moving to the left. And this is really the only addition to the fun chart. We'll talk about how acceleration factors into things in a second, but that's basically it. Questions might also ask you about the difference between velocity and speed. And they're very similar, but in one-dimensional motion there's a big difference, and the difference is that velocity is a vector. And so velocity is a vector, which means it has direction. And in one-dimensional motion, this simply means that velocity could either be positive or negative. Whereas speed is a scalar, which means that it doesn't have direction, and so your speed is always positive. So the question is, well, how do you get speed from velocity? Well, if velocity is always positive, velocity is positive or negative, but speed is always positive. How do we get something positive from something negative? We take the absolute value. And so this is a relationship that you need to know. Speed is the absolute value of velocity, and that's it. Taking a further look, let's say that we're going to integrate velocity, and we're going to integrate it between 2 times a and b. Remember back from that chart, a couple pages back, hey, if we integrate velocity, we're going to get position. Cool. So if I integrate velocity, I'm going to get x of b minus x of a, using the fundamental theorem of calculus. And this means, in words, the change in position between t equals a and t equals b. So change in position between a and b. Now, this expression right here, x of b minus x of a, this is called displacement because it only takes into account where you started, i.e. x equals a, and where you ended, i.e. x equals, or x of b. Okay? And so this is called displacement because it's basically your final position minus your initial position. It doesn't take into account how you got to there, only the difference in the 2 coordinates. Let's look at an example. Let's say you're at your house and you want to go to school. Yay. Okay. And so you start the day and you're like, okay, great, I drive to school, and I drive back home. And so at t equals a, I'm at home. This is my x position, I'm at home. And at t equals b, I also am at home because at the end of the day, I went back home. What is my displacement? Well, my displacement is like, let's say my home is at 0 and my school is at 10, because it's like 10 miles away. My displacement would be 0 minus 0, which is 0, which is kind of weird because I went to school and I came back. But my displacement is how far did I move from my original starting spot? Well, I started and I ended in the same spot, so my displacement is 0. Well, what is the thing that would be 20, right? I traveled 10 miles to school and I traveled 10 miles back. Well, that thing is called distance. And the distance that you went is 10 plus 10, which is 20. Well, how do we get distance using an integral? Let's go back to our speed equation. The fact that, because velocity can be negative, that's why your displacement can end up being 0. So if we want to find distance, we're going to integrate speed. We're going to take the integral of speed to find the distance, because speed takes into account the fact that you could be going, like, it takes away the negative from the velocity, and so therefore we can get always a positive distance. And so this is a formula that you need to know. Distance equals the integral of speed, dt. You could also just write it as the integral of the absolute value of velocity, dt. And so those are separate formulas that you need to know, separate from the displacement ones. One last thing I want to talk about is how do you tell if you're speeding up or slowing down? If you're speeding up, that means that acceleration and velocity have the same sign. They're essentially vectors pointed in the same direction. It's easier to do it in terms of same sign, so they're either going to be plus plus or minus minus. In the event that you have a graph, what you can do is you can look at the graph of velocity. So if you have a v-graph, a graph of velocity, you know you're speeding up if your velocity is getting farther away from 0. So you can be speeding up as if v is moving away from 0. That's another way you can tell speeding up. The exact opposite is slowing down. And so you can kind of think, well, slowing down is going to be a and v have different signs. So you could have plus minus or minus plus. Or if you have a graph of velocity, so if you have a v graph, then v is getting closer to 0. Okay, and that's how you tell if a particle is speeding up or slowing down. Let's look at a graph of a velocity curve and see how all these things sort of come together. All right, here's my velocity graph. I'm going to label some x values, or sorry, some t values. That's my independent variable. So we have a, we have b, which will be at the top of this. We have c, we have d, and we have e. All right, let's just first off say, when is the particle moving to the right or to the left? Well, between a and c, so a to c, the velocity is positive, v of t is greater than 0, so the particle here is moving to the right. And similarly, from c to e, v is negative, so therefore the particle is moving to the left. I'm going to write this a little bit shorthand because we're going to have a lot to fill in. So that's the first relationship you can notice. Notice that at t equals c, so at c, the velocity is 0. And because the velocity changes from positive to negative, the particle changes direction here. Because the particle was moving forwards, i.e. to the right, and now it's moving to the left. So we say that when the velocity changes sign, the particle changes direction. All right, let's look at some other things. Notice that from a to b, what's happening to the velocity? Well, the velocity is moving away from 0. Same thing from c to d. Okay, so from a to b and from c to d, because the velocity is moving away from 0, the particle is speeding up. And sort of the opposite, from b to c and from d to e, notice that the velocity is getting closer to 0. So b to c, d to e, velocity is getting closer to 0, so this is slowing down. The particle is slowing down. A few last things to notice graphically. If you have the velocity curve, notice that the slope at any given point, the slope is the derivative, and the derivative of velocity is acceleration. So if you look at the slope of the graph, the slope is the acceleration. Notice that again from a to b, velocity is positive and the slope is positive, and therefore they have the same sign. That's why the particle is speeding up. Similarly, if we were to take the area under the curve, i.e. the integral, this physical area represents the displacement, which is the integral of velocity. And so we have this, if you have a velocity curve, the slope is the acceleration, and the area under the curve is the integral, which is the displacement, because position is the integral of velocity. Hopefully this gives you a slightly better idea as to particle motion. I'll do an example problem in the next video so you can see how we can use this on real questions.